What's up, everyone? Welcome to the CVPR pre-show sponsored by Voxel 51. I'm your host, Harpreet Sahota. I'm a hacker in residence at Voxel 51. I'm joined by my co-host, Jason Corso, co-founder and CSO at Voxel 51 and professor of robotics, electrical engineering, and computer science at the University of Michigan. We're here today with Julio Silva Rodríguez. Julio is a postdoctoral fellow at the ETS of Montreal, conducting research on pre-training and zero/few-shot adaptation of large vision models. He has a special interest in vision language pre-training. Beyond broader computer vision topics, he is interested in developing foundation models for medical image analysis and studying novel strategies for few-shot parameter-efficient transfer learning. We're going to discuss Julio's paper, a closer look at few-shot adaptation of large vision language models. The paper introduces a methodology called CLAP, which is a realistic and principled approach for few-shot adaptation of vision language models that outperforms state-of-the-art methods by adding a class adaptive penalty to avoid large deviations from zero-shot prototypes without requiring per-task hyperparameter tuning on a validation set. I'm excited to talk to Julio about his work. Hope you're ready for it too. Let's get right into it.
Hello all, and thanks for having me. And in our CVPR work, we are focused on large vision language models, in particular clip-alike models that have become very popular. In particular, clip-like models present that text and vision encoders, which are pre-trained on large heterogeneous data with text description to produce joint representations on paired images and text descriptions for both modalities. So these models are pre-trained on massive amounts of data, and they have presented quite robust zero-shot inference performance. And what do we understand by zero-shot? So they produce image-level classifications on computer vision tasks based on some classification prototypes for each class, which are obtained as a text embedding for some descriptions for each task. So this has revolutionized the vision language field in the past years. And apart from this zero-shot inference, we particularly focus in the use case in which you have few annotated images and you want to get a new classifier for your downstream task. For instance, 16 images for each category. In this topic, it is quite interesting doing an efficient transfer learning on these rich pre-trained features. The most straightforward approach was using this support set, training a logistic regression linear classifier, which is commonly known as linear probing. So interestingly, differently from other pre-training fields, zero-shot performance was quite competitive if you don't have more than 4 samples labeled for each class. So to get rid from this limitation of few-shot linear probing, many works in the last 2 or 3 years have started to propose what is called vision language adapters. So vision language adapters combine the text-driven embeddings with the descriptions of the task and the support set vision embeddings, using MLP-driven representations, and finally with some sort of classifier. And this kind of methods got like quite more robust performance using only 1 shot, 2 shots, 4 shots per class. So first, our work focused on making a closer look, a closer interpretation of what these few-shot vision language adapters are doing. And by doing so, we see that vision language adapters benefit from the zero-shot initialization as the initial point during the adaptation. And finally, they balance the robustness you get with the zero-shot prototypes and the new knowledge learned from the few shots. For some categories of tasks, maybe your pre-trained model is not good enough. So in this case, you want to get more information from the few shots than from the zero shots. So if you take a closer look, you see that you are balancing the few shots and zero shots via some blending hyperparameters at some point. The problem is, how do you find these hyperparameters? How do you know if you should rely more on zero shot or on few shot? So this is our main motivation hypothesis from our work. If you only have 4 samples for each class, how do you use a validation set? Which is your validation set? In real world scenarios, you may not have validation data and you want to use all the data for training. And more interestingly, these vision language adapters like clip adapter are becoming very popular. If you do not find this hyperparameter for each task, then your performance drops if you compare it with a linear probe that is well initialized. As you can see with these cross dataset experiments, that you have in detail in the manuscript. So this is our motivation, and we try to find new solutions that have a model selection strategy, and particularly we retain the prior knowledge with some constraints so that the new class prototypes keep close to the initial solutions, but we do it adaptively for each, and in this way, we can accommodate for each task if the pre-trained knowledge is suitable or not. And we do so without any validation data, and thus it is highly more generalizable and usable for practitioners. That's a general scope of the motivation of the paper.
Thank you very much for presenting that, Julio. One of the findings I read in your paper was that CLAP is outperforming the current state-of-the-art ETL methods across 11 data sets. Can you first just briefly describe what is meant by these ETL methods and how is it that CLAP is able to outperform them?
Yeah, efficient transfer learning are black box kind of adapter methods that work over pre-trained features. They do not focus on fine-tuning some parts of the model for adaptation, but any model you have as a pre-trained model for adaptation, they just work over the features they expect. So this is quite efficient, particularly when you have, let's say, low resources, low computational resources, you can make very fast adaptation. So we benchmark with all prior state-of-the-art efficient transfer learning methods in a validation-free setting. Let's assume we don't have validation and you have to fix your hyperparameters using a common set. And this is where CLAP excels the most, thanks to its own model selection.
So Julio, do you think there's anything special about the use of CLIP as the basis for the original multimodal embedding? Like if you had swapped in Blip or some other like multimodal embedding, would you see the same results?
We focus mostly on CLIP-alike models, contrastive pre-training. What we see is that the more larger the architecture it is, and the more pre-training data you use, the better the transferability it is, which is the better the efficient transfer learning adaptation is. If you use smaller networks, not that much pre-training data, then you might need some fine-tuning. But for efficient transfer learning, it seems that training large networks, you can get very, very good performance without any fine-tuning with this efficient transfer learning method. Not in vision language, but also supervised pre-trained only vision models. We also try this kind of adaptation because you can take the zero-shot prototypes from the pre-trained vision weights, and still this kind of adaptive strategy with this works. But for vision language, we focused on CLIP and all its different architectures.
I understand that you use one prototype per class to kind of ensure that you don't diverge from the original representation. And that's hand selected or that's randomly selected? I'm really curious about this notion because I'm just thinking back to like even quite a while ago when we had these like bank type models where they were like hand selected object embeddings or action embeddings. And there was a lot of emphasis on why are you hand selecting them versus learning them, for example. So could you talk more about the prototypes that you use?
Yeah, these zero-shot prototypes are obtained with the text descriptions that for the benchmarks we use, like ImageNet benchmarks or fine-grained data sets, like we use the same as prior literature that they might be some quite often simple, like a picture of the category name. And then you get the text embedding. There are works focusing also on using more descriptions, like a template of 80 descriptions to get the average text embedding. But we just focus on using this simple handcrafted embedding of a picture of whatever it is. It is true that, for instance, prompt learning methods that are quite popular also, which also are kind of efficient transfer learning because they try to train the best embedding, the best text description. But these prompt learning methods are quite inefficiently computationally because you have to backpropagate the weights over the whole backbone, over the whole text backbone. We find that using simple text prompts, you get good performance, but it is true that in some expert applications, finding a good initial prototype might not be that straightforward. This might be a limitation because you rely on the constraint to this prototype.
And we'll round it out with for practitioners that are looking to apply your findings, what are some practical steps or considerations that they should keep in mind? Are there any specific scenarios where your methodology shines the most?
Based on our experiments, using this constraint so that the learned prototype keep close to the initial solution works especially well for domain generalization. Domain generalization is the topic in which you adapt your pre-trained model, your pre-trained vision language model to one domain, but then you expect to have domain drifts. So in this scenario, we have seen that this adaptively class constraint, it's working especially well. If you expect having some domain drifts, CLAP, it's able to retain this knowledge better than other vision language adapters in the literature.
Awesome. Thank you, Julio. Looking forward to have you back in just a few minutes here for the panel discussion.